Uh, okay, so welcome back uh, to the class with a picture of James Joule and William Thomson, who was later called Lord Kelvin. I just thought that getting some pictures of people whose names we keep hearing and who have contributed to the development of statistical physics, thermodynamics would be nice rather than they be abstract names. I don't know whether that helps much because, I mean, one can hardly differentiate between the two. All of them have beards and very indistinct pictures, but okay, that's what we have at the moment. So talking about Lord Kelvin, who, among other things, also set up the Kelvin scale. Uh, I don't know whether he set up the Kelvin scale or not, but at least the temperature scale is called Kelvin. So I will just put some clarifications. The triple point of water is actually 0.01 degree centigrade. The water freezes at 0 degree centigrade, but the triple point of water is 0.01 degree centigrade. Uh, and it has to be 0.006 atmospheres. So you have to specify both of these, and only then do you get, and of course, then volume is fixed if you have 1 mole. So if you have 1 mole and temperature is fixed and pressure is fixed, then the volume automatically by the PV equal to nRT gets fixed, and that corresponds to 273.16 Kelvin, okay, 0.001. So the 0 degree Kelvin, once you extrapolate it back, as we discussed in the last class, is 273.15. And accuracy to the second place of decimal, I don't know, it might be more accurate possible today. But this is the clarification. The triple point is 273.16. The 0 Kelvin in terms of centigrade is 273 minus 273.15. So with that clarification, I start with the content of today's class. I'll just put it here. Okay. So, adiabatically, so we're going to discuss first law of thermodynamics, basically that the relation between heat and work and internal energy. So for adiabatically isolated systems, so that there's no heat exchange, it is experimentally observed that the amount of work needed to change the state of a system depends only on the initial and final states and not by the means or path by which the work is performed. Now here, when I say work, it's just so the work is work done on the gas or on a system or by the system. Now, when this is being done, there can also be some energy losses or dissipation due to friction at the walls, right? So that is not being counted for. So here we are saying the work done on the system by the system, not accounting for an idealized system where the friction can be neglected. And then the amount of work, if there is no heat exchange, depends upon initial and final state only, right? So which means that du, the change in internal energy, is equal to dw. This is only the configurational work done, the work done by the system, on the system, no dissipation. And that's because dq equal to 0. Uh, right? So to complete, so the internal, if there's work done on the system, if we compress it, its internal energy will increase. And we know that the internal energy today we know, previously we didn't, but in this year, 2022, we know that, or 23, we know that the internal energy consists of the energy of interaction plus the kinetic energy. Now, in a system which can exchange heat with the reservoir, the first law of thermodynamics becomes du equal to the heat added. So if you add heat to the system, then its internal energy will increase. And if the system does work, so suppose it pushes some piston, right? So work done by system. So the internal is going to lose some internal energy. And this is the statement, right? Du equal to dq. It's with a cross because this is not a differential, uh, right? And in this case, uh, the change in energy will depend upon the path, right? Here it was basically the work done was dependent only on the initial and final state, but not here. Now, for ideal gas, there's no interaction between gas molecules. So the internal energy depends upon the kinetic energy of the molecules only. And the kinetic energy of molecules actually determines the temperature of the system, as we shall see later from statistical physics, right? So that's an input which comes from statistical physics. Uh, yeah, actually, never mind. It's actually related to the fluctuations, but we won't discuss that right now. Uh, we'll discuss it when the time comes, right? So the work in a adiabatic process is independent of the path of the work done, not so for this case when there is energy exchange with the reservoir. And this is dependent only on the initial and final state, which also is an indicative of that internal energy is a state function. It's a function of the parameters which characterize the system. So, what is heat? The formal definition is what the amount of energy that is added to a system, which results in temperature change but when no work is done. So there's a temperature change, something inside the system is changing, energy is changing, internal energy is changing, um, or it could decrease, is added or subtracted to a system, which results in a temperature change, but there's no work done. Now, for ideal gas, the internal energy depends upon temperature only. It does not depend upon density. There's no interaction. So if you change the volume of the system and you had the same number of particles, the effective interaction between the particles, uh, as long as it behaves like an ideal gas, is not going to change, right? If you decrease the volume too much, of course, the particles will start interacting and it will become a liquid. But we are assuming that we are working in a temperature range which is way above, high above the where the gas becomes a liquid and the gas behaves like an ideal gas. Within that range, if you change the volume, the internal energy depends upon temperature only, right? But in general, the internal energy could depend upon both temperature and volume, density of particles, right? But ideal gas, only function of temperature. Now, Joule in whatever 1942 or whenever, what he did was take a box of fluid, set a paddle inside it. It was thermally isolated. It was adiabatic, no heat exchange. And when he dropped, this paddle, which can rotate, its axle was connected by a wire or a string to a pulley. And this weight could move due to its gravity, right? It could move due to gravity and move a certain distance. That's work done, force into displacement, and that would rotate this paddle wheel. Now he allowed the same work to be done at different rates, slow rate, fast rate. So the path is in that sense a bit different. Uh, but he saw that whatever the weight W2 was dropped, the temperature change always went from T1 to T2. Why? Because as it rotated, it had friction with the fluid and it dissipated heat. So heat was generated. So work was transformed into heat by friction, by rotation of these paddle walls. And it saw that the heat dissipation due to the viscous forces always led to a change of T1 to T2. So work was completely converted into heat, Okay. Uh, as we'll see later, work can be converted into heat, but heat cannot be completely converted into work as long as, I mean, in a cyclic process. You have to take back the system to its original state because you want to keep on doing work. So you take heat, convert it into work, and take back the system to its original position so you can run it in a cyclic process, and then you can't do it. Some heat will be wasted. It will be given off to a reservoir, low temperature reservoir, right? So Joule also did a free expansion of gas experiment, uh, right? And so what he had is a box of gas connected by another box where you had vacuum of volume V2. And when this separation, when this whatever plate that separated the two boxes was removed, this gas occupied the bigger box, so the volume became V1 plus V2. But what was observed for an ideal gas, and it's extremely important that it's an ideal gas, that T1 remained equal to T2. So which means that uh, the that the temperature didn't change, the internal energy didn't change. There was no work done because this side was vacuum. So when gas expanded, it didn't have to push anything, right? So no work was done on its external surroundings. This system was kept isolated, the thermally insulated system in Joule's free expansion of gas experiment. So heat, the energy, heat is the energy absorbed when there is change in temperature and when no work is done. So no work is done. Heat was not being allowed to be exchanged anyway. The temperature remained the same. Right? So that's the conclusion, that the internal energy for an ideal gas, for an ideal gas only, is dependent only upon temperature and not density, which means it's non-interacting. I mean, I'm adding this non-interacting thing as of today because we know what internal energy is. I'm not sure whether they knew it at that point of time. The other thing to realize is, in general, U is a function of state. Then if you specify either P of B and you have a fixed amount of gas, 1 mole or whatever, 5 moles, then that itself decides the value of the internal energy. And that's not very surprising of today because I mean, so here in general, P and V means non-ideal gas as well, because the internal energy is sum of the kinetic energy plus the potential energy. So it's a function of state. That is what was realized at that point of time, thermodynamics, even before statistical mechanics came into being. All these connections of microscopics to the thermodynamics comes to statistical physics, because you calculate certain energy, average energy of the system, and then you see that it behaved same as the internal energy, what is called internal energy in thermodynamics behaved, right? So I'm discussing thermodynamics, but already using inputs of statistical mechanics, whereas that was not there. You just observe that internal energy seems to be a state function, and you don't have exact understanding of what internal energy is, because they didn't know at that point of time. There was no clear idea, and or they didn't know that there were atoms and molecules and so on and so forth, right? Uh, yeah, they had maybe a concept of a mole, but yeah. So they had a concept of a mole, but don't think it was measured in the terms of we understand it today. So similarly, other quantities uh, like magnetization. So this is the basically, mm, uh, well, this is a state function, and this is more of the ideal gas law. Sorry, equivalent to I think what are they called, equation state. So the point, I think this is irrelevant in this context, but what I want to say that there exists a function u whose differential is an exact differential. So you can write du to be a function of del u del p at constant v and del u del v at constant p, dv here and dp here. You can also choose some other function, suppose temperature and pressure, or you can choose temperature and volume. So you're free to do that, but then you can't vary three of the quantities independently for the same amount of matter of the gas, because you have the equation of state, right? It relates temperature to pressure and volume, right? And the reason we say that U is a state function is because experimentally it was established that for an isolated system, no heat exchange, the total work done, dissipation. So if this dissipation becomes a bit more complicated here, we're really talking about configurational work done on the system, which the energy can absorb, or the system does work is totally dependent on the final state of the system. So hence it's a state function, right? But in general, the internal energy can be written as the work done plus the heat absorbed. And these quantities, if there is heat exchange, uh, they're not exact differentials. Moreover, they are not only so these things are defined only when there's a transformation. It's not a property of the system. Internal energy, once it's reached equilibrium, is a property of the system. Once you fix P and V, internal energy is fixed for a certain matter, right? But these things, depending upon what path you take, can vary. The amount of heat taken in, the work done, and so on. And moreover, the work done, you can not only have the system doing work or work done on the system, but there can also be dissipation during work done. Right? So that's a completely different thing. So even if you do a quasi-static process, and if there is dissipation, then those systems are not reversible. Because if you suppose the system does some work, some of it pushes a piston and some of it is dissipated. Now, the same amount of work you do on it, there will be some friction again, and some of it will be converted into internal energy, assuming no heat, right? No heat exchange, right? And then it won't come back to its original state, right? So quasi-static processes with dissipation are not reversible. However, quasi-static processes without dissipation are reversible. So, and these processes, especially non-reversible quasi-static processes, cannot be drawn on a state diagram. But because you can take the different paths, and then you can also have you can also change things in non-equilibrium conditions. But once it reaches equilibrium, the endpoints, once it's reached equilibrium and reached a certain nu, p, and v, the endpoints of the exact functions like U, the internal energy, or the Helmholtz free energy, they can always be identified on a state diagram because they're properties of the endpoints. The other thing to note is, even though once in a while we write dq dt, the amount of heat changed on changing a temperature, this should not be considered as a differentiation. You can differentiate if Q is a function of temperature. Q is not a function of temperature. You're just saying that if you change temperature and do this kind of process, how much amount of heat is absorbed or exchanged. So it's valid only on transformation. It's not a function, it's not a state function that you can differentiate it. So we write it like this, that if we change temperature, how much heat is absorbed or released, but it's not a differentiation. dq is not a function. Q is not a function of T. Yeah. But having said that, you can basically define it. If you allow heat exchange under constant volume, then you will have a certain value, the heat capacity at constant volume. So the amount of heat absorbed to change T by unit, whatever be your unit. Let's take it to be Kelvin. Okay. Under constant volume, it will have CV, but if you do it under constant pressure, it will have a certain different value. It's heat capacity at constant pressure, right? Uh, under these now relation between Cp and Cv, but only for ideal gases. So this discussion is only for ideal gases. In general, you can write dq equal to du plus pdv. This is the first law. And you are expressing in terms of T and V. Why T and V? Because you want a relation between Cp and Cv. So you want du dt, if you like. Cp is how much internal energy is changing. Oh, okay. Under constant volume, no work done, how much and heat is to be absorbed for a unit change in temperature. Right? So that's Cv. And then this heat has to go to internal energy, right? So that's why del U del T into dt, and then you're also writing del U del V into dV, right? U as a function of T and V plus PdV. But you know that del U del T dq dt del U del T at constant volume is Cv, right? That's the amount of if you didn't allow volume to change, the amount of heat absorbed will go directly to change in internal energy. And moreover, you know, for ideal gases and only for ideal gases, del U del V at constant temperature, internal energy does not depend upon volume, right? So this quantity is zero. So what you have done is taken the dV out and written these two. So this relation becomes like this. Now this you know equal to zero for ideal gas, right? And then if you put it in terms of, okay, how much heat is absorbed, unit change of temperature, uh, you can write uh, Cv, which is coming from here, and then P del V del T, right? So how much volume changes in on uh, I mean a small change in temperature, how much volume changes, and this would be the work done, right? Now, del V del T for an ideal gas, you know, V equal to nRT, so you can calculate del V del T at constant pressure. And when you substitute that, you get Cp, the heat capacity at constant pressure, equal to Cv, the heat capacity at constant volume, plus Nr. So all that you have done is take this derivative with respect to T, and you get Nr by P and substitute here. You get already a P sitting here, so you have Nr. Now, if you do it molar, then it will be Cpm molar, Cvm molar plus R, right? So that's the relation between molar Cp and molar Cv. You might already know it, but just repeating it. So application of the first law. So again, now we are doing adiabatic conditions, and we already have PV equal to nRT. But you know, if you change an gas, uh, if you if you do some work and you change the pressure and volume of a gas adiabatically, there'll be some temperature change as well, right? So they won't be all independent. So can you figure out an extra relation? So what we do is under adiabatic conditions, um, yeah. So here pressure was also changing. Here we have adiabatic, pressure is changing, but heat is not changing. So if it's adiabatic, no heat is being added. So you have this relation du plus pdv equal to 0. And then P, you're using the ideal gas equation, and then you're substituting P equal to nRT by V. Now, you know that Cp by Cv equal to Nr, right? So you substitute that, and then you get Cp by dt Cp, and you just substitute Nr, you get Cp minus Cv here by V, and you don't even, I mean, you don't need to divide by moles. So you get this relation. Now, if you integrate it and write Cp by Cv equal to gamma, you get this relation ln T, right? So it's not, I think this is not division by moles, but it should be division by T. So this T is missing here. This T has come here. And you already had dV by V. So what you get is ln T gamma minus 1 ln V equal to constant. And from which you get this relationship, right? This whole over and above P equal to nRT. So in an adiabatic transition, and then if you substitute T from this ideal gas equation, you also get PV equal to gamma equal to constant. So if you change something adiabatically, its temperature will also change, but this relation between P and V, independent of temperature, will hold, or this is independent of pressure. This relation is going to hold for ideal gas, because we have used ideal gas equations in Cp minus Cv equal to Nr, and moreover, you have used adiabatic conditions, right? So that's now let's calculate the work done by an ideal gas in an isothermal process. Isothermal process temperature doesn't change. P1 V1 changes to P2 V2. Temperature is completely unchanged. The work done is PdV. But now P equal to nRT by V, right? So pressure is continuously changing as a function as this transition is happening, right? But here it also assumes it has to be quasi-static because you're using that volume is defined at each point. So you have replaced it by nRT by V, but doing it in such a manner, temperature is constant. So you're going to take this out and integrate dV by V. So you'll get the work done equal to nRT ln V2 by V1. And since there's no temperature change, we know that the internal energy will be unchanged if this is ideal gas. And why is this valid for an ideal gas? Because we have used the ideal gas equation to solve it, right? We use P equal to nRT by V. So in the use of this relation, we know that this is valid only for an ideal gas. If we are using some van der Waals gas, then we would have a more complicated relation here, right? So you might have still temperature to be constant, but you would have a more complicated relation. And when you integrate it, this relation will be much more complicated. So the work done by an ideal gas. Why are we so interested in ideal gas? I mean, classically, we are interested because they were using gases at high temperature to get their work done. And they wanted later to figure out the maximum work that can be extracted from heat. And at high temperatures, gases do behave like ideal gases, right? So if they closed any energy exchange, so then the work done by gas in an adiabatic process as it changes from P1 V1 to P2 V2. Remember, if it's an adiabatic process and this is happening, temperature has to change. Internal energy has to change. Then the work done can be written again as PdV going from V1 to V2. But now this P, you can replace it. The temperature is changing. So you don't want to use PV equal to nRT here because T is continuously changing as volume is changing. But you can use this quantity. And if it is quasi-static and if volume is defined at each point, right, we can do this only for quasi-static processes. Then using this relation and integrating it, and you're going to get quantities So if you integrate it, you'll get v to the power minus gamma plus 1, blah, blah, blah. And then you replace your C, right, the C by pressure, and you're going to get this expression, right? So this is the work done by the system. Okay? Now, similarly, if liquid is heated at constant volume and it goes from P1 T1 to P2 T2, note this is liquid. You can't use ideal gas equations anymore. So ideal gas is not assumed. It's liquid. Show that P2 minus P1 equal to beta by kappa T2 minus T1. So what is beta? Beta is the volume expansivity. Is defined as 1 by V del as you change the temperature, how much volume has changed, normalized by the original volume at constant pressure. And isothermal compressibility is when you change volume, how much pressure changes, or if you change pressure, how much volume changes. So it's written 1 by kappa here in terms of, because it's del V del T upon 1 by V again, 1 by T, right? So the way to solve the problem, you are being asked to calculate P2 minus P1. So you basically want dP. And how would you express pressure in terms of, so see here there is del V del T. So there's some, it's a function of temperature, and this is a function of volume. So we are expressing P in terms of T and V. How if you change temperature, how will pressure change? If you change volume, uh, how will how will volume change? Right. Uh, Now, what you do is at constant volume del P del T. So at constant volume, yeah, so this was written at constant volume, but you use this relationship. I think it's called, I've forgotten whatever it is called. They teach you in first year mathematical methods course. So this is the some circular relation or something it is called, and then this relation will holds, right? So you convert your del P del T relation and you replace it, you del P del T, you replace it by the other two terms, and then you do a bit of manipulation, integrate it once the things become constant, and you get P2 minus P1 equal to beta by kappa T2 minus T1, right? So this del P del T, because you don't have del P del T here, right? But here you have. So here this you replace in terms of other quantities, right? Moreover, this term is not going to contribute because you said that liquid is heated at constant volume. So this is not contributing, only this is contributing. And then you replace it by the suitable formulas using the cyclic relationships so that you get del V del T expansivity, del P del V. Then you introduce this V and V, it will cancel off, and you will get this relationship, right? So that's the end of this class. These are some ways we did some problems to have so that you have a handle of how to use first law of thermodynamics. Then we'll move to the second law of thermodynamics in the next class. Okay. So what do we do? First of all, stop share and